All right, let's get this going, Rob. Hello,
All right.
everyone. On behalf of the Education and Training Committee here at CETA, I'd like to welcome you all to today's webinar. The committee's been working hard over the past few months to launch this webinar series as part of our ongoing mission to provide meaningful and accessible education to the CETA community. We're excited to bring forward timely and practical content that supports professionals working in controlled environment testing, certification, and compliance. Today's webinar, entitled Beyond Containment, Current Issues in Fume Hood Testing, will be presented by Rob Chopowick, who's an experienced professional with deep knowledge in this area. Rob will walk us through key concepts, challenges, and testing methodologies involved in certifying fume hoods. Whether you're new to the topic or looking to refine your existing knowledge, there should be something here for everyone. Before we get started, I'd like to share a couple quick points. For those who have technical issues during the presentation, please use the chat option to communicate with the office. For those who have questions that you would like to direct to the speaker, please use the question box. And a survey link will be provided in the chat and will be emailed with the presentation. We would appreciate if you could provide your feedback. And with that, I'm going to hand it over to Rob.
Well, thank you, Dan. Appreciate that. Good afternoon, everyone, and welcome to today's webinar on fume hood testing. I'm Rob Chopwood, and I'm excited to be here as, I guess, the first CETA webinar. And for that, I do want to say thank you to the CETA executive for allowing me to be here, to David Phillips, your president, to Abby Roth, and to Dan, of course, and all the others on the executive and the committees that work on these things. They do a great job. So it's an honor to be here, to be part of that. Now, today I'm going to share some insights on the current landscape and the future directions in this field of fume hood testing. Uh, I'm going to talk about where we are today, how the standards compare, and what's on the horizon. So here's what was advertised about today's seminar. It's very official and very intriguing, and perhaps, but I have to admit, if I presented a seminar the way this is written, and don't get me wrong, I wrote this, but if I had to present in a very official and intriguing way, I would fall asleep. It's fume hoods after all, so it's tough. You got to raise the game. So here's what all of that means. Basically, I'm going to spend most of the time today, about 50% of the time, talking about the current state of ASHRAE 110 testing and how and what's been going on with that. Then I'm going to be talking about, or we'll look briefly at the North American standards and how they're all connected. And we'll focus for a short time on the European standard. We'll do that'll take about 25% of the time. And then finally, we'll discuss emerging technologies and their protocols. Now, to be fair, these are not really new, as emerging might suggest, but they're emerging in the sense that the adoption rate of these new technologies or methods seems to be growing. And at the very end, we'll do a very quick high-level interview. Now, what today is not going to be about, it's not going to be what a fume hood is, reviewing different types of fume hoods, how to test a fume hood, or how to become certified in testing fume hoods. None of that. I also want to put out a quick disclaimer that some of the images in this presentation were taken from the web and others were created by AI. Nowadays, if you can kind of see which ones are AI created, they're very intricate. So maybe you can spot them here. And the other thing is, this presentation is from my perspective, and I'm happy to share what I have and what I know. And opinions of others may vary. I've been in seminars and conferences where people have talked about what's going on with ASHRAE and the standard and that sort of thing. And I sit on the committee, and I don't really miss too many meetings, but sometimes I hear these things coming out, and it's not even close to what I know to be true. It's I appreciate the effort to try to communicate and share. So that makes me believe that everybody has their own perspective on what's happening and what they see. So I just want to preface everything. This is my perspective of my involvement with the ASHRAE committee, my involvement with fume hood testing over the last, I guess, 15 years or so, and the last 10 years for sure inside the ASHRAE 110 committee. So let's kick off with part one of this. We'll delve into the ASHRAE 110 standard. Now, this standard's been around since 1985, and it consists of three basic tests. phase velocity, smoke visualization, and tracer gas. Now, many simply refer to this as the mannequin test. And for good reason. It's the standout piece that whenever you're doing a full ASHRAE 110 test, you're bringing a mannequin, you're doing tracer gas, and the mannequin becomes the topic of conversation. Now, there are some issues with ASHRAE 110. And although the tests are very standard, they do present some challenges. For phase velocity, there are limited locations and they're done one at a time and it's done over a short period of time. For smoke visualization, both large and small volume both the large and small volume variations use the same locations, which is a little bit confusing. And the bottom line with smoke visualization, it's subjective. And for the tracer gas testing, it specifies SF6, but it does allow for other gases. But there's a lack of repeatability, which we'll talk about later. And it only uses static locations and brings in dynamic challenges when requested by the customer. So it has some issues. So what I want to talk about mostly today is what's been going on with the ASHRAE 110 standard to address those issues. To understand the recent developments with ASHRAE 110, we have to jump back to 2013. And this year was notable because it was the year when, unfortunately, we lost Nelson Mandela. It was also the year of the Boston Marathon bombings, a very unfortunate event, and a much less important world event, but important to the world of tracer gas testing. That was the year in which the state of California, which has been in the news quite a bit lately, but in 2013, the state of California banned SF6. So that changed our universe of fume hood testing, or so it seemed. Because why, I guess the question everybody has and had was, why is SF6 such a bad thing? Well, the thing is, it's a synthetic gas and it's highly resistant to the natural processes that the earth and the atmosphere have for removing these greenhouse gases. So unlike other greenhouse gases, SF6 doesn't break easily. Now, nature's way of getting rid of greenhouse gases, it has a bunch of ways. From the earth, it has the forests, the oceans, and even the soil and rocks. They all play a role. The forests will absorb carbon dioxide. The oceans, they'll dissolve it into the water. And the soils and rocks will actually hold it away from the air. Another process for removing greenhouse gases is atmospheric based. It's just up in the air and it happens entirely under the sunlight, where the sunlight helps break down molecules. Basically, ultraviolet radiation is breaking these greenhouse gases into simpler compounds like water and carbon monoxide. There's another one. It's called it involves something called the hydroxyl radicals, and these are like little tiny Pac-Man. And if you haven't been able to spot the first AI image, this would be it. Now, these guys, little Pac-Man, they're like nature's atmospheric detergent. They break down pollutants, specifically greenhouse gases, and they absorb or eat the garbage that's up there. But SF6 is robust, and these little guys have a hard time with SF6. And like I said, they are known as hydroxy radicals, but tiny Pac-Man seems a bit easier to remember. Now, here is AI image number 2. The SF6 is a pretty robust little molecule, and as the numbers show, it's quite a stark story. SF6 has the highest global warming potential, 24,000 times that of CO2, and it's 35% more than the next guy. Now, also, it lives in the air for 3,200 years. That's a long time. So these SF6 molecules, by staying in the air that long, being synthetic, they hold a lot of heat. And that is fundamentally the issue. This is a table that I'll just show briefly, showing various types of greenhouse gases. And the bottom row, you can see that it is just a distinct difference that sulfur hexafluoride has and why it's been targeted as a problem. Now, this problem led to a bunch of stuff happening in the early 2010s to I'll say to 2017. There were various studies about alternative tracer gases, and so they started looking at alcohol mixtures like ethanol. It could be vaporized, mixed with air, and discharged from the current equipment that we use to do tracer gas with. And then they were also looking at things to detect it because there were some issues with the cost of tracer gas testing. And so looking for more affordable alternatives. So photo ionization detectors were found to be useful to a certain degree. So a lot of focus was spent on what kind of alternative through an alcohol mixture would be good, what kind of detection device would be good. So before I go any further, I just want to talk about these PIDs because uh, a bit of a spoiler alert, they are I guess, where we're going with detection of alternative gases and vapors, that sort of thing. But there are some pros and cons. Um, Now, the PIDs have been around for some time, and the problem was they weren't really sensitive enough to handle SF6. So we had other instruments like the Moran Sapphire, the infrared detector. So through infrared optics, they could detect the gas at a very low level. And we also have what used to be the USON leak meter. It's now the Qualitaire 200. And that instrument is also a very strong instrument in the sense that it can detect very low levels. So the PID wasn't quite at that level, but at least for the gases. But for vaporized alcohol, it was found that this thing actually could work. It does have some issues like it's sensitive to changes in humidity, and it still may not be sensitive enough at low levels. So it's not the perhaps the ultimate solution. Maybe there's a custom solution that's out there to be designed for tracer gas testing, but right now these I, these PIDs, it's easier to say, um, are the way we're kind of looking at where we're going to go. So, what we have is, as we were doing this testing, we learned that there was a story when they were doing all this research on what kind of alternative gas and what might be a good detector. So, in the laboratory where some of this research was going, um, they were evaporating ethanol and among other gases. And like all labs, there's a lot of IPA kicking around, and they do a lot of cleaning. And so try to make sure everything's cleaned in between so you get a good clean environment for your next test. Well, as the story goes, that during a cleaning process, somebody kindly noticed that these PIDs were going a little berserk. And well, during this cleaning process, so kind of made the connection that the vaporization or the fumes from the IPA were actually getting picked up quite well by the PIDs. So the focus of the researchers got shifted a little bit. Um, and so IPA became kind of a number one sort of thing to search out. So in 2017, ASHRAE launched Project 1573. Now, this was a research project designed to test out the concept of IPA, test out the concept of PIDs, basically, and find out an alternative tracer gas. And in 2017, something else also happened. The Moran Sapphire, the infrared detector, the manufacturer said, we're not making it anymore. So then it became an issue. We definitely have to find an alternative detection device. So this research project went on, and they had a couple of key findings. The first was that the repeatability of test results among different ejector diffuser systems was not what they thought it was going to be. It was a surprise because if you look in the standard, there's a specification how to build the ejector and diffuser, and it's right there. And you ask any engineer who's been part of that or involved in it, well, you can't go wrong. Well, you can go wrong. So there was a problem with the ejector. And what they noticed is the ejector provided different plumes of gas coming outside the ejector. And when you have a different plume, it was discovered that did have a significant effect on the result of the test. So here's a picture of the traditional ejector and diffuser. So the ejector is the base at the bottom, and the diffuser is the crown at the top. So you could, depending on where you positioned the tubing, where if it was close to equipment, close to the front, depending on whether or not that top crown, it's a screen. You can't really see it well here. If it had denser holes, that could affect the plume. And the orifice itself in the ejector, over time, that could wear and that could affect the way, affect the output of the diffuser. So looking at this, and then all of a sudden some tests were done side by side with various diffusers. And the result was that, my goodness, these things aren't as standard as we thought. The second key finding was that vaporized IPA was found to be the most effective among the alcohols they were testing. But there was an unresolved problem, and that was how to safely vaporize it because it has an inherent risk. It is flammable, and unless care is taken, vaporized IPA can be a fire hazard. And that's not a problem we ever had with the SF6. So a user-friendly, safe, and repeatable method was needed. So what do we do? Well, in 2020, the ASHRAE 110 committee, we began the journey to update the standard. We started by discussing the results of the research project. We talked about the need to develop a reliable vapor generating device for IPA. And we figured once a workable device was created, we need to do some sort of testing. And we decided that we were going to do some round robin testing of this new device. And the big thing was the deadline for getting all this done was in 2024. Now, the IPA vaporization device, that development was taking some time. So as we moved out of 2020 into 2021, it was a challenge. We did some testing, but getting a workable alternative that we could prove out, that was a little tough. Uh, there were some people leading the way. They were doing a great job, but work still had to be done by the committee to work it into the ASHRAE standards. So even though we started in 2020, we had a deadline in 2024. As we're moving into 2021 and later of the year, we needed some time to be able to get all that information and work it into the standard for the revision. So time was getting tight. And because for anybody who's worked on a committee, you know it's not a fast process. So with time getting tight, uh, we some people in the committee were starting to wonder what are the options we can pursue. Well, coming along kind of out of nowhere, although it's been used by some manufacturers in the past, was propylene gas. So this was put forth as an option. Now, initially, it was kind of this might be good because sulfur hexafluoride is a compressed gas, as is propylene gas. Propylene has a bit of an issue, though. Like IPA, it has a flammability hazard. And so, even though it appeared initially to be something we can consider, there is that risk. So I'll talk about that risk in a little bit, but the other thing that came along with the propylene gas was a new ejector. Now, this isn't how it looks. I was going to put it in, but I realized I'm not sure about patents and patent pending trademarks on the new design. Some of you may have seen it, I don't know, but basically it is a new device that is a way to it's ideally going to work with anything that we have, whether it's IPA, whether it's propylene, and even SF6. It would replace the whole ejector. So my apologies for not having that new design to show you. But again, with trademark issues and the people designing it, I want to respect their right for that. So we had the propylene testing come in, and we didn't have any research on it. Now IPA, we had the research project 1573, but propylene not so much. So the committee, we agreed to do round robin testing. And what that meant was we had the ejector and we had propylene gas, and we went around to all the committee members, and if they had a lab or access to a lab, we did the testing ourselves. The results were positive, and the correlations with sulfur hexafluoride were surprisingly good. Problem was, even though we were testing it, it just wasn't a robust enough testing process. So more testing is needed, more validation is needed. So although we were enthusiastic about it, when we got to the end, we realized it just wasn't defensible enough in terms of research, like the way the IPA research had been done and how much better from a defensible point of view, the IPA research really was. So here we are. We have the alternate tracer gases that are in this race to find the best one. We have SF6, IPA, and propylene gas. Now, you can see the lower and upper levels for IPA and propylene gas. They're around 2%. Anything below 4% is a bit of a hazard. So the flammability is a real risk. If you're working in a lab, if you're a manufacturer and you're doing testing in a lab, you can mitigate that risk fairly well. But when you're talking about field testing, you're shipping stuff around the state, around the country, wherever it is. And sometimes you got new field testers out there. And if you've got a process that has a risk of fire or flammability, as someone who sent field testers out to do fume hoods, I know I would not be comfortable in all cases, especially with a new technician. So we are aware of these concerns, and that is going to be considered. And I know the researchers are working on ways to make this as safe as possible. But ultimately, the IPA and propylene gas using PIDs and new ejector, um, well, the IPA you can purchase in Walmart or Walgreens, and it's very affordable. Propylene gas is not as expensive as SF6, but it's sort of in between. So now I just want to jump ahead to 2025. And what's interesting through all of this is that back in 2013, when California said no more SF6, we're 12 years later and nobody else but California has made that the rule or the law. There are some areas in the Northeast US where they are trying to get more involved in phasing out SF6, but nobody has committed to it. So despite all this work for 12 years to deal with SF6, it's still a viable gas that can be used in every place but California. Up here in Canada, where I'm from, it's a standard gas. And so for now, SF6 is going to continue. Now, as of 2025, the designs for the ejectors and diffusers, well, they're well on their way. I would guess we're 90 to 95% there. The 3D printing technology has really helped enhance the development of the new ejector. Um, but there are still some considerations needed because, as we did with the previous standard, when the specifications were written very clearly from an engineering point of view, that doesn't always translate into a perfect product on the other end, depending on who's reading the specs or who's fabricating the end product. With 3D technology, maybe we can have more confidence in the standardization, but that's still an issue that we need to work out. So what finally happened is that the committee, much to its dismay, a month or two ago, we had little choice, but time was running out, so we had to reaffirm the existing standard. Um, so as it is written, that is still the standard to be used. So that is the wandering down the journey of what's happening with ASHRAE. Now, moving to part two of this presentation, I want to compare different fume hood standards, both North American and European. Now, what I've got here is I've created a visual for how standards like Z95 and OSHA and NFPA might inform the government standards like NIH and the California's regulations. But the thing is, it's all underpinned by ASHRAE. ASHRAE is the basis upon every other standard out there in North America. In fact, here's the same kind of structure for Canada, where I'm from, as I said. Um, we have our CSA Z316.5, which is our main non-government standard, and we have our government standard of the MD 15128. Again, same standard, and everything is based on ASHRAE. Um, the one problem, though, is, and this is always been an issue with ASHRAE, and anybody who's gone out and tried to do fume hood testing and their customers want ASHRAE testing. It was never meant to be a certification standard, a lot like the NSF 49 standard for biosafety cabinets. ASHRAE 110, and it's in the name itself, which is unfortunate. It's a standard method of testing. It provides no criteria for pass or fail. You can argue there is wording in terms of smoke visualization test, but really the standard as a whole is about how to test, to tell you how much of something you have in a reliable, repeatable way. Um, so that meant other standards had to be developed, and that's why they really exist, to provide more guidance on what is an acceptable level of performance and containment for fumets. Now, here's the thing. If you read the ASHRAE standard, you will not find a single mention of Z9.5, OSHA, NFPA, NIH, nothing. But when you read any of those, you will find all kinds of mentions of ASHRAE 110, and that's the difference. ASHRAE 110 is the granddaddy, the foundation of everything, and that's why it's so interesting for me as someone who's been in the industry to be on the committee and working with this. It's extremely interesting, and the people there are very smart. So I do have high hopes for us finding a very good solution to alternative gases and alternative devices. So ASHRAE 110, North America, it's the one. But as big as it is in North America, when we cross the pond, it's not really used. It is known in the European fume hood community, about the same way we in North America know about their standard. Many of you maybe have heard of the EN 14175 standard. And that might be it, or maybe you've never even heard of that. The fact is that there are two different communities of fume hood testing. There's North American and the European. The European standard is broken down into multiple parts, covering vocabulary, safety, performance, test methods, on-site test methods, installation, and what have you. Now, for anybody who's done some clean room testing, say ISO 14464, it's broken down into different parts for clean rooms. So this is also an ISO-driven standard, so the structure is very similar. Now, one thing is that EN 14175 utilizes tracer gas, like SF6 or other alternatives, but it defines some minimum phase velocities and it defines stability criteria. It also outlines SASH design, some ergonomic features for manufacturers as they develop and build these things, and it includes requirements for alarms and SASH stops and maintenance accessibility. So here's a direct comparison of some selected items between ASHRAE 110 and the European standard. So the European standard focuses a lot on safety. ASHRAE, not so much. The European standard likes to put in some tests that would disturb the environment in the lab. In the ASHRAE standard, they are optional, and we'll talk about those a little later. And with ASHRAE, we do the sampling outside the hood. We have the mannequin, and we do one single point of sampling of any leak gas right in the breathing zone of the mannequin. In the European standard, sampling is done on a matrix of many sample tubes outside the hood, plus there are a number of ejector tubes inside the hood. And I've included this image to see that we use a mannequin, but the Europeans do not. What they have is almost like a spider web, if you will, of tubes all funneling in to a central round bucket. We'll call it that for now. And so that's where I think the biggest difference between the two. And there's been discussions, but they're not a big fan of the mannequin, at least the way it's currently being done. And North Americans aren't a big fan of their approach, the way it's currently being done. Now, a common question is whether we'll see one international standard for fume hood testing. Short answer is not likely in the near term. Now, discussions have happened between the leading representatives in the European community and the North American community, but the differences in the approach and the existing regulatory frameworks kind of make the idea of a unified standard something of a distant prospect. I would say for most of you in today's seminar, it probably will be beyond your time in the industry when we ultimately get a unified standard. Now let's move on to part 3A. Let's talk about these emerging trends. There are four that I've chosen that I just want to talk briefly about. And these are the minimum flow measurements, laser flow visualization, dynamic challenges, and multi-zone sampling. Now, there are other emerging trends, but I thought in terms of selecting just some, these were the ones that I selected. Now, the minimum flow. This is an interesting one because it really, when you step back and think about it, it basically says, is there enough air being extracted out of the fume hood so that you will not get an accumulation of any toxic vapors or gases? in the fume hood that would create problems for the user or the lab. When you look back, okay, at the existing tests, we don't really have a really good handle on making that kind of measurement. Years ago, NFPA had uh, a minimum flow of, I believe it was 25 CFM per cubic foot of work surface. And they changed back over 10 years ago to going to air change rates of about 150. But in some cases, that was still kind of low. So there is some work being done on determining what the minimum flow should be and how you measure it. And right now, the way that's going to be measured is measuring in the duct. Now, in this image of all these ducts above fume hoods, those are actually ideal situations where you can access the duct to do a duct traverse and measure the exhaust flow. But for many of you who've done these things, you know that exhaust ducts are not readily accessible. So it's going to be a difficult thing to really get down into a standard test. But I really think this is an important safety element of the test protocol, and I'm hoping to see at least some big steps towards standardization of this test coming in the near future. The next range of new tests is dynamic challenges. Now, if you, I got to admit this, I tried to use my graphic skills and superimpose some dude walking across some fume hoods here, because one of the challenges is a walk-by test. And basically all you're doing is walking in front of the fume hood, creating air disturbances. Now, these tests are described in ASHRAE in the appendix, and they're described in the other standards to varying degrees. But in terms of are they absolutely required, what we find is depending on the customer, depending on the standard, they are effectively optional in most cases. Some other tests that I have not shown here are room pressurization tests, where you open and close the doors to the lab, because that does change the pressurization in the lab, and that can cause a sudden pull of toxic chemicals or air from the fume hood, and perhaps even just excessive airflows if you've got diffusers or the HVAC system is really strong for whatever reason as they're perhaps building a new wing in a research facility. We're simulating with fans right in front of the hood. Now, that's been part of the manufacturer's test for a while, but that's starting to creep more into the field testing as well. So these robust tests or robustness tests, that's got a category within the EN 14175 that includes a variety of disruptions to the airflow. But here in North America, we're still looking at it as optional for the most part. Now, this next one is a laser flow visualization. Laser flow, it's a fascinating technology. It's not emerging, although I've got it as emerging because it's not really well accepted in the testing community. I remember years ago, I ordered some lasers from Germany, and they came in little tubes. I had three colors, and we stuck them on the side of the fume hood, and we created smoke, and it was quite a show. And I was talking with the manufacturer about that, and I said, "Hey, I'm coming to do some testing at your site. How about I bring the lasers, and we just see how they are?" And then actually, what was I guess it was a customer, not a manufacturer, and the customer had a lot of fume hoods, and we brought him out, and the laser show was very informative. The problem was that it showed a lot, and we realized this shows a heck of a lot of movement around the face, and without truly understanding what we've got, this technology to be implemented in a standard where everybody would come to the same conclusion about what you're seeing. It's not that easy, but I think it's got a lot of potential. And as an alternative to greenhouse gases or flammable alcohols, vaporized alcohols, lasers from a safety point of view really has a lot of potential. And I'm looking forward to seeing how that can be evolved into a standardized testing process. Um, and the next thing is a multi-point zone sampling. And this is more driven by the EN 14135 standard, 14175 standard, I should say, because they've got so many sample points outside. It only makes sense that you look at more than just one. So it doesn't take a whole lot to sort of understand the logic of that. It just provides a more comprehensive picture of containment across the entire opening of a fume hood. So as we get to the end here, the final part, I just want to wrap up and talk a little bit about the role of artificial intelligence in fume hood testing. Now, here this table shows that AI is already starting to play a role in several areas. For sensor data monitoring, AI is evolving towards real-time, automated, and continuous processes. Manufacturers are incorporating AI into automated controls for SASH, airflow, environmental adjustments. And now we have predictive maintenance is also starting to emerge through data analytics and alerts. But tracer gas testing, for the person doing the testing, it's not really there yet. It's still manual based and detector based. Certainly, transferring the data and analyzing the data, that's got all kinds of AI potential written uh, all over it, so that when you're getting the data, it can be analyzed with a multiple of variables. Maybe the standard variables that we know about, maybe custom variables that belong just to the customer at that site. So there's a lot of potential there. But certification, or rather fume hood testing, because we don't really certify a fume hood unless you've got specific pass-fail criteria. But that being said, testing fume hoods remains a human-led exercise, although AI can support data collection and it can assist with regulatory compliance. So in the near term, say next 2 to 5 years, what are we looking at with AI? Well, it probably will be streamlining data logging, um, be involved in pattern recognition algorithms, and maybe that might be a big assistance to helping identify providing clear direction for laser testing coupled with AI recognition of patterns. That might be something that could be pretty cool. Um, and we'll have image and video analysis, optimizing hood and sash positions and airflow conditions for standard optimized test. And AI will also help calibrate models using real test data, enhancing predictive maintenance and risk assessments. One thing I didn't put in here is drone technology. And it wouldn't surprise me if somebody decides to put on a detector on a drone and have that run in front of a fume hood. Um, Now, in the longer term, and maybe the longer term is where drone technology might fit in, but AI will be continuously learning from the test data, adjusting for variables like cross drafts, user behavior, and room occupancy in real time. It will integrate chemical hazards and the data of chemical hazards with dynamic airflow testing, and that can help virtual risk assessments, so we can dive deeper into the risk assessments on a hood by hood basis, even before we get into any physical testing. And we'll see fume hood performance data integrated with building management systems. Are we going to see a little robot like this little guy doing the testing? Entirely possible, because that's really what a drone could be. But there is going to be an element of the human factor here. So how should humans adapt to this? Well, you hear everywhere. I'm not telling you anything you haven't heard or seen. Upskill in AI literacy, know when to trust what you're seeing and understand. It's crucial to maintain a critical oversight. Understanding, like I said, when to trust it, how its decisions are made, and how to interpret these unexpected results. And finally, with AI, it really is important to try to understand the nuances of how that would work with different setups. And this is all human stuff. So human expertise will always be vital to the trends in fume hood testing, but I do think where we're going with this, with the new ejector, the new gases, implementation of AI, and working towards an international standard, I think the future of fume hood testing is very interesting. And I can tell you from when I started, it's gotten the levels of interest of interesting things has gotten scales and scales higher. So I think it's a great industry to be in right now. And I think with that, I'll wrap it up. Timing is, I think we're just about on time. And I want to thank all of you for listening to me go on. And for any follow-up questions, I'm happy to receive your emails. But I think I'm going to turn it back over to Dan, because we have a Q&A session happening now. Dan, are you there?
Yep. Hey, Rob. Yeah, thank you. Looks like we do have a few questions coming through. Let's see. I see some coming in. We've got the Q&A. We've got a couple in the chat. Um, Ductless fume hoods. Do you have anything on ductless fume hoods that ASHRAE doesn't cover?
Ductless fumets. No, that's a growing thing in the industry. And I can speak being Canadian. I'm also the chair for the Canadian Standards Association standard, the Z 316.5. And we've addressed that's been a growing thing. We're addressing that in our standard. And I believe other standards in the US are starting to address that more. Um, it's not going away, but it's important that anybody who's writing about it and trying to implement it into a standard, understands the limitations. And I think if you talk to all the manufacturers of ductless fumelets, they'll be the first to say, "Hey, we have limitations here. Don't just treat this as a normal fume hood." So right now, I don't see it as being something I haven't heard that it's something we're going to implement into the ASHRAE 110 standard. Uh, Certainly, the next revision of the standard, where we hopefully get all these things completed, there might be room to open the door to that. But as it stands now, I think those questions are best answered in the Z95s and all those other standards that are above the ASHRAE or resting on the ASHRAE.
All right,
Okay.
thank you. Got another question. Is there an estimated time frame on the latest ASHRAE 110 standard?
Okay, well, we just reaffirmed the standard for 2025. So they are generally 5, 10 year cycles. I think I can't say if we're going to try to redo it within 5 years. I would think that's the logical objective. I can't speak for the committee or ASHRAE on how we're going to move forward with it. All I can say is that we did not, much to our dismay, get everything lined up and ready for publication in the current one, which will be, uh, I guess, republished, but just it's a reaffirmation of what's there. So I think we're looking at a minimum of 5 years before we have anything new. And so it's we're close. Like I said, the ejector is almost there. We've talked about a number of gases. We are so close, and the meetings where we voted on whether or not to reaffirm or to try to bring this new stuff in, those were very well discussed meetings. And I know there was a lot of people who were disappointed we couldn't go forward this time. So 5 years, I think, before you have a new standard beyond what we have today.
All right, great. Thank you. Let's see. I've got another question here. How do you recommend a company that doesn't have a Moran start ASHRAE tracer gas testing? Sorry, I'm not familiar with that term, but
Okay, well, the Moran is the infrared detector. Formerly, or it was produced by Thermo Electron. Yeah, and they stopped making them. You can buy them used. That might be the most cost-efficient way to get in, to be able to follow the existing standard. But finding places to service them, that's becoming an issue as well. So there is another product out there, and it's called it's a leak meter, whereas the Moran was an infrared gas detector. This is a leak meter, different methodologies. It's the Q200. It's the only one out there, so it's not like I'm playing favors with a manufacturer. There's only one. It's the Q200, and there are distributors for those. So I encourage you to look at that as an option. But if you want to be very aggressive, I know that the people pushing the IPA and doing a lot of work in that research, they're actually successfully using it with PIDs. So that is already happening. I myself have not used it because I haven't had to do any testing in California. But in California, where anybody who's going there, they've had to go to these alternative methods. So it's a tough question to answer. Easiest, probably try to buy a used one, a used Moran, or um, or buy a new leak meter. And that way you can still follow the SF6 protocol.
all right, thank you. Looks like we do have time for a few more questions. So if you can't see them on your end, I'll go ahead and read a few. How often should a fume hood be inspected?
Well, most standards will say at least yearly, and that's probably the minimum. If you're doing, if you think about fume hoods, they get plugged into a building. And so you're not just looking at changes to the fume hood. In a biosafety cabinet, you have, uh, there are conditions for if you move the biosafety cabinet, you got to test it again because you don't know what's happened. Fume hood gets plugged into a building, and a lot of things can happen over the course of a year. So it's very easy to argue that a year is a long period of time not to double check that your fume hood, which is your primary safety device in labs that have them, uh, to have it done twice a year, that makes more practical sense. But I also know there's a cost to every test that's done. So for a lot of owners of fume hoods, that's not practical, but at a minimum, once a year. And I think most standards or most regulatory bodies, they will use that as their guideline. Now, there is one thing, tracer gas testing. There's a big difference between the cost of just doing face velocity testing and smoke visualization testing, because you don't have to do all three of the ASHRAE primary tests. You can choose. That's always been there. And choosing to do the ASHRAE test with tracer gas, that's a big cost consideration. So not everybody is keen on spending that money. Some organizations with a lot of fume hoods, universities, government agencies, they will set up maybe a rotating schedule of maybe doing a tracer gas test every 5 years, which means 20% of your fume hoods every year are getting a tracer gas test in addition to the other tests. So minimum annually, and with tracer gas, that's going to depend on budget. But definitely, I've seen standards when you get it for the first time, you should have the full deal done. Tracer gas and all the smoke tests and velocity so that you know what you've got. No matter how it performed in the manufacturer's laboratory, you've plugged it into your building and you want to know that with all your building's conditions and variables, it works the way you need it to.
All right, great. Let's see here. All right, got time for one or two more, I think. With the energy sector using SF6, what is the estimated percentage of SF6 release from USA fume hood testing compared to the energy sector?
Ah, good question. I don't have the number. All I can say it's our industry, what we put out there is insignificant compared to the energy use. Now, for those of you who may not be aware, the biggest user of SF6 in North America is our energy sector. It's used for insulating power lines and a few other things that I'm not that familiar with. But I'm not sure they've even been able to nail down a number. But what I can say is it's virtually insignificant compared to what is being put out there. However, that being said, SF6 is still a greenhouse gas. SF6 is still a bad greenhouse gas. And so, as long as we're using it, even though it's insignificant, we're still part of the problem and not part of the solution. So, I'll leave that right there.
All right, thank you. Let's go with one more. Is there any push to make airflow disruption mandatory in the states? Um, this might be incredibly important to identify any micro exposures.
Um, It's hard to say if there's any push. I can tell you from the ASHRAE committee right now, our push is not on those robust or dynamic challenges. Our push is on alternatives right now. That being said, I've been involved in many tracer gas projects where putting dynamic challenges in place, whether it's fans, um, walk-bys, or opening, closing doors, or adjusting room conditions in other ways. Uh, it's an emerging thing. And so that's why I've included it in my four emerging sort of methods. I think it's important, and I think you'll see more of it. And it's just a matter of coming to terms with a standard way, because right now there's a little variation in how you do the robustness tests. The European standard has defined it. We're a little more loose, a little more flexible. Maybe flexible is a better way of saying than loose. But I think it's important. And any customer who asks for it, I think that's a smart customer.
All right, great. Thank you. Um, I think, let me see if I can grab one more quick question. Uh, do you know if California will accept the the N2O as a viable alternative?
Okay. To Honestly, I'm not familiar with the California regulations um, for N2O or dioxide. Um, but it's certainly within ASHRAE, any alternative gas, um, provided you can generate it in a consistent way, and it's written in the standard specifically or what's acceptable. But even though it tries to be specific, the end result is it's really hard to be able to say, oh yes, the plume that this gas generated, it mirrors the SF6 plume, and the results are comparable. That's hard to say. It doesn't mean that alternative gases aren't being used, and I would say only the most experienced people in the field are able to effectively use these alternative gases, because you really have to have a sense for uh, when a leak might be significant and when that threshold is going to be. Um, but unfortunately, I don't live in California, and I don't know all the details of. I'm sure it's available publicly. If N2O is available for use and in what conditions, I would think it probably is. But it's not specifically written anywhere as an alternative. So
All right, sounds good. Well, I think we'll close this one out. First and foremost, Rob, I would like to thank you for your time. And I think you kind of hit the nail on the head in the beginning of this, talking about, keeping people entertained and awake during a presentation as fun as fume hoods. But I will say that you did a really good job keeping me awake. Thank you for that.
there's one.
Uh, I do want to thank CETA and Capitol Hill Management. They provided all the technical resources to put this on. The E&T committee that I'm chair for, we've been pushing this webinar series. We have some upcoming webinars for Q3 and Q4, which will be announced. Um, and then as far as the survey link, that'll be posted in the chat. That will also be emailed alongside the presentation slides within probably the next 48 hours. This webinar recording will also be posted to CETA's YouTube channel. And for those of you who are wondering, yes, CETA does have a YouTube channel. There's no content on there yet. This is going to be the first upload there. So be sure to check it out. We'll either send the link there or post it in the chat, but be sure to check out the YouTube channel and subscribe for updates.
Right.
So that's it. Thank
Thank,
you,
th
Rob.
Thank you, Dan. And I was going to tell a joke early on. I never did. It was a time travel joke. You guys didn't like it. Anyway, I'll let that sit for a bit. All right. Thanks, Dan.
What, you're going to tell a joke? All right. Thank you.
Okay.